Oh, hello, everybody. Um, nice to see you again. With spring break and the current situation that we're under, I didn't get a chance to review exam one, so I thought I would give you a couple videos real quick review for that and help us prepare for the final. So let me switch over here and share my screen with you. And then I will show you currently, the results of the exam. As you can see, the average was 75, which is acceptable. About 60% of the class passed. And then you can see the breakdown of the questions. First question was pretty close to being acceptable. I think 70 is my target. Second question was good. Third question, you guys were all over that one. That was the simpler of the two shear force and bending moment diagrams. And the last one was a little more challenging. The score was a little below. So we'll just go through those. It takes a little bit longer, so I'll probably use the first four problems on one video and the second half on the other. So let me switch to my overhead view. So there's the breakdown again. And let me slide over here and we'll begin the exam review. So there's the test. It happened way back on March 5th. You might remember that. It was Thursday before spring break several weeks ago. And let's look at the first two problems. So here's problem one. I'll put problem two up there also, and we'll just do a quick little review. So what I'd like you to do during the exam is to look at the two problems that you have to solve, in this case for truss analysis, and decide which one you want to do. So let's just take a minute to do that. The four forces that I'm interested in, three occur right here on this strip. And then the fourth one is this vertical member right here. On the second one, again, I have a similar scenario where three of the forces are in one plane, and then there's one here. So right now they look very similar. If I make a cut here, I can look at the small side method of sections, or I could also use method of joints and work my way in. So that would be a possibility. On the second problem, I could cut here, do method of sections, or I could also try some method of joints. That might be a little more challenging with method of joints. So right now, I don't really see much difference in it. The majority of the class, basically 78%, like question one. So let's look at question one. So I'm going to make my cut here, exposing these three elements, as you can see, and then I've got this vertical component this way. So when I cut, I'm going to look at the right-hand side. I'm really interested in this reaction. So the first thing I did is look at the free body of the whole structure and found my reaction at EY, 4.5 kilonewtons there. Also, I just looked at it and I noticed that DF, really, if I look at joint D, well, that's my classic case two. I've got two concurrent members. So therefore, this member here, the DF member, is a zero force member. So I got that one a lot easier. Didn't have to do a lot of work. So when I went ahead with EY found, I drew a free body diagram of the right-hand side, as you can see here. And these are my three unknown forces, FG, EF, CD. So in looking for places to do my moments, I noticed right away that FG, EF, they have F in common, so I'm definitely going to do F. Then I've got CF, CD, so I'll do C. And one that's not completely obvious right away is that CD and FG are concurrent here at E. So I'm going to use that for my third position. So going back, let's start with the moment about F. I decided to do my moments about F. The remaining unknown CF only has a horizontal component, so that's pretty easy. Force times distance, and then my reaction times distance too. So that's pretty easy to solve for CD. I got 9 kilonewtons, so that's tension. Now I do C, a little bit different thing to worry about here is when I go about C, these two forces are easy, but I got to do something with FG. You need to slide it around. I decided to slide it up to F And at F, only the horizontal component would create moment. And the horizontal component, this is a 2-to-1 slope, so the horizontal component would be 2. So that's how I get the 2 square root of 5. So that's the horizontal component of FG. And then at 2 meters, that's the height here. And then the other forces are easy to find at their moment arm distances. And I solved that, I got 6.7 kilonewtons. And then when I finally go down here to E, see here I have E, well, I have to worry about how I'm going to handle the unknown CF. So again, I can put that anywhere I want on the line of action. I decide to let it slide down to C. And when I do that, I have a vertical and a horizontal component. The horizontal would pass through E, so I just have the vertical component. That's also a 2-to-1 slope, so that'll be the one side. So you can see I've got the 1/5 of CF. And then since it's here, it'll be this distance, which is 4 meters. And then the only remaining one would be 3 at 2 meters. And I found that one at 3.35. So that was problem 1. Problem 2, the strategies are pretty much the same. When I identified the 3 that I wanted here with one cut, I decided the left-hand side was a little bit easier. So here's my free body diagram of that left-hand side. I realized I needed the reaction at A. So looking at the entire structure, summing moments at C, I found my reaction at A. It's just a few forces to account for. 1, 2, 3, 4. If you take your time and go through those, you'll find your reaction is 2. Then I put that 2 here at the pin, and then I'm looking at this free body diagram of the section cut. I've got 2 that are horizontal, 1 that has horizontal verticals. This one's gonna be a little easier to do than the previous one. In fact, you can see right away DE, BE, AB. So let's see, A, those have B in common, so B would be a good place. DE, BE, E would be a good place. And then when I'm done, I just have BE left. It's the only unknown with a vertical component. So I'll just sum forces in the Y direction. So let's go through that. So starting with B, I just have to worry about DE. There it is, creating negative moment. And then I have a bunch of other forces to account for. One here, and then the reaction. So I found that DE was compression of 2 kilonewtons. Then I went to some moments about E, which is here. So I have to worry about AB, and really, no, there's nothing else. Everything else passes through E, so really that was easy. AB was 0. And then I'm left to find what I need for BE, and I'm going to do that by summing forces in the vertical direction. I looked at my slope here. It's a change of 1 to 1. It was 3 to 3, so that's 1 to 1. So I'm looking at just the vertical component 1. That's 1 over the square root of 2. So there's my vertical component of BE. And I've got 6 down and 2 up. Easy to find BE. Compression, 5.66. So the last thing I need to do is find this last force AE, which is this vertical component. And I just noticed here at A, it's a pretty easy free body diagram to draw off the joint A. I just have a horizontal component AB, which I've already found, and this unknown vertical component AE. If I look at it, that's pretty easy. Some forces in the Y direction, AE is -2 kilonewtons. And that's problem 2. All right, so now 3 and 4 are to find shear force and bending moment equations. So again, I'm gonna use the same strategy I did before. I'm gonna investigate problem 3 and problem 4 and see which one is gonna be a little easier. So let's see, problem 3, I've got a continuous load. That's a good thing. But this reaction is gonna force me to write one set of equations for 0 to 6 and a second from 6 to 12. So that's 2 I have to write. It's a pin, a little less work to find reactions at a pin. Problem 4, I got shear and moment. It's a little more work, but again, discontinuous load, so I have 2 locations. I'm not sure which of these problems would be that much easier. My experience has shown me that students are kind of a little leery of linear loads, and that was shown in your response. You'll see that problem 3 and 4, overwhelmingly, most people worked problem 4. The few that did work problem 3 didn't fare as well. So again, we're having issues with being able to write the equation of a linear line. So let's start with that one first. So I want to find my reaction here. This is a pin, so I just have by. So I sum moments at B to find my reaction AY. The concentrated equivalent of this load, triangle, 1/2 base 12 times height 4, that's 24. Centroid's 1/3 the distance from the big end. Well, that'd be 4 meters. And then with that information, I can easily find the reaction at A. So now I'm going to come back, I'm going to cut the structure here. And the left side of that cut's a lot easier than the right side. So there's my left side free body. So the first challenge here is at some arbitrary distance x, what's the intensity of the load? And that's just the equation of this line. Line that starts off with an intercept of 0, I just need to know the slope of this line. And slope is rise over run, 4 over 6, 1/3. So the value right here is x over 3 for any value x. So therefore, this concentrated equivalent force is triangle, so 1/2 base x, height, x over 3. So I get a force of x squared over 6. And you can check that. If you think x is 12, you put 12 in there, you get 24, which is the same value we got earlier when we looked at the whole structure. So now with all that information, I'm just going to sum moments at the cut. Using right-hand rule, I have the moment I'm trying to find. About that, the force creates positive moment, force times distance. There's the distance third, that's the distance to the centroid. And that's it. So solve for the moment, I get x cubed over 18. And that works. At x is equal 0, I have no moment. You can see I've got no moment there. For the shear force, I'm going to sum forces in the y direction, up positive. So my shear force is down negative. My load is down negative. Easy to solve for the shear. And a quick check, if I do take the derivative of the moment with respect to x, I do get the shear. So that's a nice thing. Also, when x is equal to 0, I have no shear. And you can see at x equals 0, there's no shear at the end point. So the second part of the problem would be to cut the structure here, left or right. Again, if you look at the left side, it's a triangle. The right side would be a trapezoid. Those are a little more troubling. So I'm going to stay on the right-hand side. I'm sorry, the left-hand side. So here's my left-hand free body at some distance x. Well, there's my load from A. And that's at 6 meters. So then this variable segment would be the total distance x minus 6, x minus 6. I know the intensity of the load here is still x over 3. So my force is the same. Of course, the range of x is different. Here it was 0 to 6. Here it's going to be 6 to 12. The new thing is I have my reaction here at this 6 meter point. So when I sum my moments, I get the same thing I had before, you can see, but with the additional component of the reaction. And there's my moment. I didn't expand it. You could if you like. I just left it alone. Save a little time. And then I sum forces in the y direction. Up is positive, so my shear is down, my force is down, my reaction is up. I solve for the shear, I get this value. And again, if you do a quick check, the derivative of the moment is the shear, so that's good. One other thing to notice is that the point where they share, point A, they should have the same moment. So if you put an x equals 6 here, and you put an x equals 6 here, well, first of all, the x equals 6 cancels this out, and you can see the two equations are identical. So that's going to match. The shear equations are identical except for the addition of the 16, and that's because as you go from left to right, the shear does jump up the amount of the reaction, which is 16, and that's reflected also in the equation. So that looks pretty good. I'm pretty confident that those are correct. Okay, the fourth one, problem 4, this one everybody liked. I guess it's maybe a little easier amount of work, I'm not sure. So I started off by finding my reactions for moment and shear at the fixed connection. So I sum moments. There's my unknown moment, and there's the moment for all the different components. The force here, the additional 10 kip force at 6 feet, there's an 8 kip force at 10 feet, and then the moment at the end. So I got a negative bending moment of 216 kip feet. That seems reasonable. The whole beam is in negative bending moment. and there's my reaction. Again, seems reasonable. So I'm cutting my structure here. I decided to work the left-hand side, so there's the left-hand side. Now, I got a little lazy here. I didn't sketch in the distributed load, but I know the area under the rectangle is just base times height. Base is x, height is 2, so just 2x, so there's my force. Of course, it happens right in the middle. There's my shear force, there's my bending moment. So I sum moments at the cut, and I'll get this expression here. One thing to check is I know at x equals 0, I should get the bending moment, and x equals 0 knocks out the first two terms. I do get negative 216 kip feet, which is the bending moment. And then some forces in the y direction. I assumed up is positive, so shear is down, load is down, reaction is up. I solve for the shear, I get this. Again, another quick check, derivative of the moment, I do get the shear. And also at x equals 0 here, you can see my shear is 30, and that's what I have. That's my reaction, or my shear at x equals 0. Now I'm going to cut here, a left side or right side. I think here the right side is clearly a little bit less work. So again, I cut it at some distance x. I look at the right-hand side, positive shear force, positive bending moment. There's my applied load and moment. So now I'm summing moments at the cut. The internal moment, there's the force times its distance, and then the applied moment. Easy to find. I didn't expand that. You could obviously get a little simplified expression. And then there's some forces. I have up for shear, down for 8. That's a pretty easy one to do. Also, I can take the derivative of my moment, and I do get the shear, so that seems to match. So I feel pretty confident that those look pretty good. So to keep the video from being a little too long, I'm going to take a pause right now and let you take a pause too, and maybe take it in, and then look at the next part for questions 5, 6, 7, 8. All right. I will see you in a minute.